Whether you're a frequent visitor to busy commercial spaces or someone who seeks comfort in your own home, it's important to emphasize that HVAC systems play a crucial role in creating pleasant and healthy environments. As mentioned in the ASHRAE Fundamentals Handbook, it's essential to understand that poor air distribution can have adverse health effects and cause discomfort, regardless of your location. This inadequate air distribution is directly linked to how air is directed to the terminals of the HVAC system. Air terminals, such as grills and diffusers, play a significant role in controlling air distribution in the environment. Grills, for example, direct air in a more concentrated way at higher velocities, whereas diffusers evenly disperse air over larger areas at lower speeds. However, it's important to note that the control of air distribution to these terminals is carried out by the air ducts, which connect these terminals to the main ventilation unit of the system. Therefore, proper sizing of air ducts becomes crucial to ensure that the airflow is conducted, meeting specified flows for each area related to the HVAC system, without producing high noise levels. Consider, for example, a situation where you want to condition a space with two distinct areas. In the first area, you aim for an airflow of 900 cubic meters per hour at a velocity of 5 meters per second, while in the second area, the requirement is an airflow of 300 cubic meters per hour with the same velocity. Since volumetric flow rate results from the multiplication of velocity by the cross-sectional area of the duct, as per the continuity equation, it would be necessary to divide the main duct into two sections with distinct dimensions for each area. Now let's take a practical look at an example in AutoCAD. Just as in the previous case, following the guidelines of the ASHRAE Fundamentals Handbook, it's possible to divide an air duct into multiple sections based on the quantity and location of air terminals in the system. Besides that, the main duct can be branched, making the system even more complex. To size the ducts, one of the simplest methods is known as the velocity method. In this method, we establish velocity limits for each section of the duct, so that the duct dimensions are directly related to the total airflow rate in that section, according to the continuity equation mentioned earlier. The total flow rate in a section will depend on the sum of the specified airflow rates for the terminals connected to that specific section, as well as the subsequent sections. But here's the crucial point. When dealing with air conditioning systems that have many sections and branches, sizing the ducts can become a somewhat more complex task. Duct sizing can be like to assembling a puzzle, where each section influences the others. It's necessary to carefully choose the dimensions of each section to maintain the air velocity within the established range. Furthermore, it's essential to be attentive to abrupt variations in velocity and area that may occur from one section to another. So, doing this manually, even through a spreadsheet, can be a bit boring. For this reason, to make this whole process more accessible, I will demonstrate through an example how you can perform duct sizing in a simple and effective way using a Python code. The link to the code will be available in the video description. Let's suppose you've already performed the thermal load calculations and selected a self-contained unit to air condition a facility with 4 rooms. For rooms 1 and 2, you've decided to install 2 diffusers each with an airflow rate of 360 cubic meters per hour. In rooms 3 and 4, you've opted for a single diffuser in each, with an airflow rate of 720 cubic meters per hour. Now the next step is to create a line representing the air ducts, connecting the selected equipment to each of the diffusers. We'll divide this line into sections separated by nodes, numbering. Each section of the main duct will be numbered with tuples, starting with 0. For branches connected to section 1, for instance, you'll use tuples with 2 digits. The first digit will be the same as the section it's connected to, and the second digit will start from 0. If you need to add a new branch to section 1 to IRO of the main branch, simply repeat the first 2 numbers and start numbering the third from 0, and so on. After numbering all sections, you should enter in the code the sections where the terminals are located and their respective airflow rates. In this example, I'll input the sections where the diffusers are positioned. Finally, to complete the duct sizing process, it's necessary to add 3 essential parameters. The first parameter is the length of each section, which should be organized in ascending order. This applies not only to the sections where the terminals are located, but to all sections. For this example, we can organize the lengths as follows. The second parameter concerns velocity limits. According to the engineering toolbox, commonly used limits are 4 to 7 meters per second for main ducts and 3 to 5 meters per second for secondary ducts. The third and final parameter involves the height and width limits of the ducts. The maximum height limit depends on the availability of space in the ceiling for duct installation. In this example, we have a maximum limit of 0.5 meters. The minimum height and width limits should be set based on the diffusers and other equipment that can be added to the system. It's important to avoid connecting a diffuser that's 400 millimeters wide, for example, to a duct that's only 100 millimeters wide, which would not be appropriate. Once you've filled in all the necessary parameters in the code, all that's left to do is run it. The code uses the Scipy library, a tool that helps us find the best set of areas for the duct sections. It does this while considering all the restrictions you've specified, such as velocity limits and height and width sizing. Besides that, the code is designed to avoid abrupt changes in section area and velocity from one section to another, ensuring an efficient and balanced air conditioning system. But there's still one thing left to understand: pressure loss. Pressure loss represents the reduction in pressure or total energy of the fluid as it flows through a system due to various factors, such as frictional resistance, changes in fluid velocity, and alterations in system geometry. There are 2 main types of pressure loss. Frictional losses. This occurs along the entire length of the system and is primarily caused by the fluid's friction against the internal walls of pipes or ducts. Local losses. This type of pressure loss happens at specific points in the system, such as bends, valves, connections, and other components that cause abrupt changes in flow direction or fluid velocity. So far, the code only considers frictional losses, which, according to Frank White's Fluid Mechanics book, can be calculated by the following equation. The friction factor is a function of the Reynolds number, relative roughness of the duct, and its shape. This parameter can be obtained with a small error using the Alt-Schultz-Zoll equation. To calculate the friction factor in rectangular ducts, you can use the Hubscher equation. In this equation, A and B represents the width and the height of the duct. With the necessary parameters in hand, we can calculate the pressure losses for each duct section. According to Frank White's book, when dealing with a set of sections connected in series, the airflow rate is the same in all sections, while the total pressure loss is the sum of the pressure losses in each section. In the case of a set of sections connected in parallel, the opposite occurs. The flow rates in the sections are different, and when added together, they result in the total flow from point A to point B. However, the pressure drop is the same in each tube. To achieve pressure balance, the total pressure loss must be the same in each combination of inlets and outlets through which the air can be conducted. If the total pressure loss in one path is lower than the others, it's possible to add a device called a damper. This equipment will act as a localized pressure loss in order to achieve the pressure balance. As a result, the code will generate a table with the duct section identification, dimensions, flow rate, and pressure loss for each section. Also, the code will provide the total frictional loss for the set of sections or paths of the air ducts, along with the maximum and minimum pressure losses. The code will also return the average air velocity, considering all sections of the designed system, and the minimum required structural material area for duct fabrication. And that concludes the results for our example. At the time of recording this video, the code I'm using, which you can find in the description, is in version 1.0.0. The code can be further improved to make it more efficient and accurate. If any errors are identified, they will be corrected. I'm open to any feedback and contributions from those who are interested in collaborating with the development of this code. Soon, I will create a video explaining how you can do this through GitHub. Thank you for watching. If you've made it this far, Please subscribe to the channel for more videos like this and visit my GitHub to explore other similar projects.